For the past decade, PCI technology has served as a ubiquitous I/O interconnect solution for computing platforms. First introduced in 1992, PCI is based on a parallel bus model with initial connectivity of 32 parallel signals operating at 33 MHz. In order to scale performance with computing requirements, the industry has either increased the number of signals or increased the signal frequency. After a decade of improvements, however, the parallel PCI model is reaching its limits, making further performance enhancements expensive, less reliable, and more complex while restricting design flexibility in delivering PCI connectivity. Here we see the effects of signal skew versus clocking due to increased frequency. Increasing the number of signals further exacerbates clocking issues by augmenting the number of signals that must be synchronized with the common clock. A new alternative for I/O connectivity is required. PCI Express technology has been developed by the industry to address the needs for the next decade's computing and communications I/O requirements. Based on a serial model, clocking data at 2.5 GHz via two differentially signaled half-duplex lane pairs of wire, PCI Express technology addresses the fundamental issue of performance scaling by encoding clock and data into a single stream utilizing SerDes silicon. As a result, we are able to increase signaling speed significantly while dramatically reducing the number of signals. The resulting reduction in pin count increases design flexibility while creating more efficient and cost-effective I/O solutions. PCI Express technology was designed to utilize the extensive industry investment in software development by featuring backward software compatibility with legacy PCI infrastructure. PCI Express architecture will be used in a wide range of design platforms as a chip-to-chip and chip-to-adapter technology. Desktop and notebook designs will utilize PCI Express slots and connectors, along with Express card modules to deliver efficient connectivity solutions and true plug-and-play capability. These benefits are offered while simultaneously enabling an enhanced graphics performance roadmap and the transition to Gigabit Ethernet. By scaling the number or width of links, PCI Express technology can scale performance to enterprise requirements. The PCI Express specification enables multiple link widths, or presumably up to 80 gigabits per second of link performance at a 2.5 gigabit per second signaling rate, and can be further enhanced through signaling rate increases. Scaling width and frequency within a serial infrastructure does not have the same limitations as discussed in a parallel model due to each signal containing encoded clock and data. Servers are expected to utilize PCI Express technology via slots, server modules, and motherboard implementations. Next-generation modules and motherboard configurations deliver new flexibility in server motherboard design, aiding in delivery of dense rack mount and blade servers. By matching the performance requirements of 10 gigabit per second interconnects, PCI Express technology enables balanced server platforms, freeing processing power from traditional I/O bottlenecks. PCI Express technology also extends PCI's role in the communications industry. Within an internet infrastructure, PCI Express technology will be found embedded in traditional communications applications as well as extended into new interconnect uses. Initial PCI Express implementations will transition PCI-based connections to the higher performance and lower pin count offered by PCI Express designs. The industry is moving forward to PCI Express solution delivery in 2000.
If you're working with a relatively new computer, then it most likely is using SATA connections to plug in the storage devices inside of that computer. Here's an example of one of those. This is a 256 gig solid state drive that is using SATA connections to be able to communicate. We'll look closer at what that might look like. SATA stands for Serial AT Attachment, that AT attachment being that older AT computer, one of the original style computers, and we've kept the terminology through the years. Although the original computers are well beyond us, we have this serial AT attachment to have some comparison back to the older parallel AT attachment, or PATA. We have different standards for SATA. One of the original SATA versions was version 1.0. It ran at 1.5 gigabits per second. There's also another standard, which is the SATA revision 2.0, which is running at 3.0 gigabits per second. The latest SATA standard goes even faster than that. That's SATA Revision 3.0 that runs at 6 gigabits per second. One thing you have to watch for is occasionally you will see people abbreviate 3 gigabits per second as 3G. We can sometimes confuse 3G with third generation. That's not really the case. I've been very careful here to show you SATA Revision 1, SATA Revision 2, and SATA Revision 3, and then the speeds of those being 1.5 gigabits per second, 3 gigabits per second, and 6 gigabits per second. So if you're looking at standards for SATA, make sure you don't confuse any of that terminology. It can become confusing when you're dealing with different versions and different speeds, but as long as you synchronize those up, you shouldn't have a problem. One of the advantages that SATA brings to the table is that the connections are much smaller on the motherboard. You can see one of the older IDE or PATA connections on this motherboard, and this motherboard also has SATA connections, 1, 2, 3, 4, 5, 6 different SATA connections. If you were to look at these cables side by side, you'd really see the difference. PATA uses these larger ribbon connections. Here's the SATA connections, a much smaller connector on the motherboard and a much smaller cable that's being used to the storage device. So for the purposes of managing cables inside of your computer and making sure that the airflow is maintained through your computer, SATA has some distinct advantages. This is the back of a SATA drive, very similar to the PATA in that your interfaces are on this side. It's actually this very small interface is the SATA data connection. This larger interface is actually the power for SATA. You've also got these jumpers, and then you have an older traditional power connection. This drive was built for a computer that may be transitioning between PATA and SATA, and they gave you the option you could either plug in with the newer SATA power or on the drive. If you have an older power supply, then you would plug it in very much like this picture shows, where you still have the same data connection, but you would use this legacy Molex power connector to make sure the drive was operational. The abbreviation SCSI is pronounced SCSI, and this stands for Small Computer Systems Interface. It was a method of connecting storage devices in, at that time, were small computer systems or personal computers, and it was one of the very first ways that we had standardized storage on our computer systems. We were able to do quite a bit with this. We could string a number of devices together. They could be hard drives, they could be optical storage devices, and we could put up to 16 devices on one of these SCSI chains using a single cable and a single SCSI controller. So you were able to just put one interface in your computer and simply hang off the back of that interface 16 different devices. Through the years, there have been a number of different kinds of SCSI formats. You may see it called fast SCSI, ultra SCSI, there's ultra wide SCSI, there's ultra 2 SCSI, and so on. All of these formats tend to be backwards compatible, but the best possible performance you're going to be would be to get a storage device and a controller that were using the same type of SCSI interface. Before USB came along, SCSI was really the standard for connecting our peripherals together. We would plug in printers, scanners, tape drives, CD-ROM drives, anything that needed an external connection. SCSI was the format that we were using. On these SCSI buses, we had different sizes. We had a narrow bus SCSI. Some SCSI was a wide bus. The narrow bus could plug in 8 devices that we could string onto an individual controller. The wide bus allowed us to have 16 different devices on a single controller. The part of SCSI that really makes it powerful is that the interface and the communication itself is very, very intelligent. It's very powerful. We're able to do a lot of different communication over that SCSI bus, and it was very simple to plug in. Even though we were able to control so many diverse kinds of devices, it was a single type of interface. We assign a number to it, and now we've got a SCSI connection on our computer. SCSI has been around for a very, very long time. But even today, especially in large server farms, we see SCSI interfaces for hard drive controllers, and especially on virtualized environments, we see a lot of SCSI being used. Even though it's not a physical SCSI connection, we're still using that SCSI standard of protocols to communicate over these virtualized systems. One particular piece of SCSI that was very important, especially early on in SCSI, was the termination. You could plug many devices in, but the last device had to have what we called a terminator on the end of the chain. That way, the SCSI communication knew exactly where the signal ended. Without a terminator, none of these devices would be able to operate properly. The newer SCSI devices tend to have these terminators built into the device, and you can enable or disable the terminator just by clicking a button. But the older devices needed a physical terminator that you would connect to the interface that was on back of the SCSI device. There are many different types of interfaces that you'll see for SCSI. They've changed quite a bit through the years. Here's an example of one. You can see this one happens to be an Ultra 3 SCSI connection, and you can see a PATA connection right next to it. They're almost the same size. The SCSI might be a little bit shorter. This is a view from above. If we were to look at it from the side, you can see the interface connector is a little bit different than the PATA or the SATA connections that we've used before. This SCSI connection has quite a number of pins associated with it. The cable that we would use to connect this would be something like this, where we would plug into the motherboard, and then there might be many different connections on that same cable where we could use all of these different SCSI devices and plug them all in at the same time. If we were to look closer, you can really see a lot of different pins being used. And on this particular SCSI connection, it was a higher bandwidth, so it needed a lot more pins to be able to communicate. But it may not be this type of connection that you would see with SCSI. Because they've changed so much through the years, you might see a DB25 connection that looks like a serial, or maybe even an older parallel connection. They all look very similar, but these are actually SCSI connections. You have to look very carefully to see the differences. Some connections are very clear that they're SCSI. This high density 50-pin connection has locks on the side of it that connect in. That's very, very exclusive to SCSI. And some of these higher density connections as well really make you see that very quickly that's a SCSI connection. There's nothing else that looks quite like those connectors. When you're physically connecting SCSI devices to the SCSI cable that you have, whether they are inside of a computer or outside of a computer, you have to give each one of them a completely unique number. This is called a SCSI ID. So on that single bus, on that single connection coming out of an interface of a computer, we would provide different IDs. For instance, if this was your boot disk, maybe we'll give that SCSI ID 0. If there's a floppy disk or a scanner or an optical device, we might assign that a number 2. If there's a CD-ROM, we might assign that with a SCSI ID of 3. There's also a concept within SCSI connections called a logical unit. So within each physical SCSI ID on that interface, you might have logical units inside of this. This was very common to see if you were plugging in an external SCSI storage device that had multiple hard drives inside of it. You would give the storage device itself a SCSI ID, and then there would be logical units assigned to the individual drives within that single physical device. You also see this quite a bit when you're working with virtualized systems. As I mentioned earlier, the signal that is at the very end of the SCSI bus has to be terminated. There might be a physical terminator, or it might be a termination functionality that's built into the hardware itself. If you ever see what we call SCSI attached devices that are serial attached SCSI, they don't have jumpers, they don't have terminators, they don't have settings. A lot of the more modern storage devices that we are plugging in over something called serial attached SCSI are completely automated in the way that they configure themselves on that SCSI bus. Here's an example of a legacy SCSI device. I think this is an optical device, but it could be a hard drive, it could be a scanner, it could be anything else. Generally, we see two different types of connectors on the back of the device. One of them generally is the connection going in. You can see it written on the back of the device, where we would plug in the in connection from our computer. If we had additional SCSI devices, we would use this out connection to keep the string going, to keep that daisy chain going throughout the connection. If this was the end of the line, if this really was the last device in this SCSI chain, this is where we would plug in the terminator. If this was a device that had the termination built in, there would probably be a connector on this device, or a button you could push to say this was the terminating place. And you can also see the SCSI ID number built right into this as well. There's little buttons that would allow you to change that SCSI ID. So when this device plugged in and communicated across the SCSI bus, everyone know that this device was SCSI ID number 6. Once you have everything plugged in, it looks a little like this, where you have a SCSI controller that might be ID 0. Here's SCSI ID 1. That's a hard disk. Here's another hard disk. And they're all chained together with different SCSI IDs. And at the end of the chain is a terminator. Usually these terminators even have a little light so you can see that they are active. Here's a picture of what a SCSI terminator might look like so you can look at the back of your devices and see if you have one of those. That term daisy chain actually came from this idea of taking daisies and connecting them to each other, and you could wear them as bracelets or wear them on your head. And that same daisy chaining was how we came up with this idea of plugging in all of these devices one to the other to create that chain of devices. The back of the SCSI drive looks very similar to the back of any other hard drive. It's just using a very specialized SCSI connection on the back. Usually you have jumpers that can help you designate what the SCSI ID of this drive happens to be. And here's traditional power that you might find so that that drive can be powered up on the inside of your computer. This was an external device, then you have external power. You usually have options for setting your SCSI IDs that we saw on the SCSI device earlier, and the interfaces for going in and out of that SCSI connection. The connection of the SCSI device on your motherboard looks very similar to PATA in that we've got a connection on the motherboard and multiple interfaces on SCSI. But of course, with PATA, we are limited to 2 individual devices, whereas with SCSI, especially the wide bus SCSI, I can connect up to 16 devices, and you would simply find the closest connector to you and plug it in. It doesn't matter where along this particular cable we plug in our SCSI device. The determination of how this device communicates is associated with the ID that you assign to the SCSI device. So you simply plug into the closest connector to you and plug in all of your different SCSI devices, make sure they have different SCSI IDs, and your SCSI communication is now complete. Once you follow those rules, SCSI is very simple to get running, and it's going to provide you with a lot of flexibility to plug in multiple storage devices.
Hi, my name is John Gulbranson, and I'm the president of International Test Instruments. In this presentation, I will talk about the history of PC buses from ISA to PCI Express. So, it all started back in 1981 when IBM created the original IBM PC. That machine used a Intel 8088 CPU running at 4.77 megahertz, which resulted in the blazingly fast I/O bandwidth of 4 megabytes per second. The ISA standard, however, was created a few years later in 1984 when the PC-80, the improved PC, was created, which used the 8286 CPU. And that CPU uses a 16-bit data bus running at 8 megahertz for a total memory and I/O card bandwidth of 16 megabytes per second. There are 2 versions of the ISA card. The original 8-bit, which was used for the 8088 or original IBM PC. And you also have the 16-bit extended cards from the PC-80, which is technically only the ISA bus. The original one is not technically part of the ISA standard. Only the 16-bit one is actually spelled out in the standard, but commonly we call both of those card versions the ISA card. So depending on the actual CPU used, the 8088 or the 286, you can address either 1 meg or 16 meg of address range on the CPU bus and therefore also on the I/O card. Both of these CPUs support 64K of address space. One of the problems, of course, is that the ISA bus is not very fast. It was an old design from 1980, essentially. And after about 10 years, when Windows came along and other GUI-based operating systems, the I/O bandwidth was not enough to support the advanced graphics cards that started to come along. So the graphic cards manufacturers came together and through their group, the VESA group, Video Electronic Standards Association, created a VL bus, or VESA local bus, which essentially was again a direct attachment of the graphics card and any other card, I/O card that you wanted to directly connect with high performance, and they connected it to the CPU memory bus again. And because the top of the line CPU at the time was the 486 CPU running at 33 megahertz, that was the bus standard for the VL local bus. And the problem, of course, with doing that is that they married it to the 486 CPU bus protocol, and when other CPUs came out, particularly the Pentium, it used a different bus protocol, and the VL bus was no longer an option. It simply didn't work. Later on, IBM tried to create a future-proof and CPU-independent alternative to the ISA bus as part of their MCA microchannel architecture design. And we'll talk about that bus and the VL bus in some future slides. This slide shows the original IBM PC80 motherboard from 1984. This is the board that uses a 8286 CPU. And you can here see the two different slots. This is the legacy original PC slot, and this is the extended, you see the extension here, connector for the actual ISA slot, which is part of the ISA standard from 1984. So technically this is the only true ISA slot, but we refer to both as ISA slots and therefore ISA boards. So in this slide behind me here, you see the pinouts of the ISA bus connector. This is the whole connector for the that is spec'd as part of the 286 computer, and this part here is the original PC connector, the 8-bit. You have 8 data bits on this connector, and you have another 8 on this. So in total, you have 16 for the whole interface.
Inside every computer is a central processing unit, and inside every CPU are small components that carry out all the instructions for every program you run. These components include AND gates, which only allow electricity to flow to their output wire if all their input wires are on. The AND gates use tiny transistors to control the flow of electricity to the output wire. The electricity from another part of the computer flows in from the top and gets stopped at the first transistor unless its input wire is on. When that input wire turns on, it causes an electric field to form around a small piece of insulated metal. This electric field reaches out past the insulation and causes the properties of the semiconductor material below it to change, turning a small part of that semiconductor into a full conductor, bridging the gap for any electricity flowing in from the left and out to the right. The types of components you create from transistors are based upon how you wire their inputs and outputs together. If you chain them together so that the output of one flows to the input of the next, then you are creating an AND gate, where all the input wires must be on for the final output wire to be on. Inside the Scott CPU, you'll see a number of these AND gates scattered around, with some having more inputs than others. Another type of component that you'll come across is the OR gate, which is represented by this shape. Instead of chaining the output of each transistor to the input of the next, you instead run all the output wires to the same place, the output of the whole gate. In this way, if any of the transistors have their input wire on, then electricity flows straight through them to the gate's output. You'll also see a number of these OR gates scattered around the Scott CPU. By the way, the Scott CPU comes from the book But How Do It Know by John Scott, which is available at his website, buthowdoitknow.com. It includes a great explanation of how computers work for beginners, and John was kind enough to allow his CPU design to be used in this video. The other basic component you'll see in any CPU, including the Scott CPU, is the NOT gate. The NOT gate uses a transistor to divert the electricity already flowing to the output of the gate to a ground wire, effectively short-circuiting the output wire, turning the output of the gate off if the input wire is on. There are a number of these NOT gates inside the Scott CPU, not only in the locations seen here, but also inside the other components. For instance, the stepper component is just a particular combination of AND, OR, and NOT gates, where the output wires turn on in sequence each time the input wire to the stepper turns on. This input wire comes from another small component called the clock, where the output wires turn on and off again very quickly in a steady pattern. The only other component used in this part of the CPU is the selector, formed from another combination of AND, OR, and NOT gates that turn on one of several output wires depending upon what input wires are on at the moment. In another area of the CPU is the arithmetic logic unit, which includes more AND, OR, and NOT gates, along with the selector component that we just saw. There are a few other components in the ALU, like the exclusive OR and the NOR gate, but these are just made from the same OR gates we saw earlier, along with some AND and NOT gates. In other videos, we'll see how these components work together to process instructions sent to the CPU. This has been a brief look at what's inside the CPU. The first component is the control unit, which is kind of like a captain in the Army. It receives its orders from RAM in the form of an instruction, and then breaks that instruction down into specific commands for the other components. One of the most important components under the command of the control unit is the arithmetic logic unit, or ALU for short. The ALU is what performs all the mathematical operations inside the CPU, such as addition, subtraction, or even comparison like we saw earlier. The arithmetic logic unit has two inputs. We'll label them input A and input B, and assume they are two numbers from some previous load instructions. Now we might want to add those two numbers together. The control unit receives that instruction from RAM and then tells the ALU what type of operation to perform. The ALU performs the operation and then outputs the answer. Sometimes, though, depending upon the type of instruction, the output from the ALU can actually be ignored. For instance, if you have a compare instruction, the ALU doesn't need to output an answer. Instead, it just needs to tell the control unit how the two numbers compare to each other. For this, the ALU uses what are called flags, and they help the control unit decide what to do when it receives the next instruction, like jump if, which we'll see later. For now, though, let's say that we are working with an instruction that does produce an output. Where does that output actually go? Well, the 8 wires coming out of the ALU would actually run to what is called a register. A register is a very simple component whose only job is to store a number temporarily. Registers act just like RAM, except they are inside the CPU, making them faster and more useful for storing a number temporarily while an instruction is being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register's set wire. The set wire is just like the one we saw earlier for RAM. When the set wire is turned on, the register saves whatever number is on its input wires. Once we have the output saved in the register, though, how do we get it back out? Well, when we are ready to move a number out of the register, we need another control wire called the enable wire that also runs from the control unit to the register. As soon as the control unit turns the enable wire on, the register will output whatever number is saved inside. The output wires of the register then connect to what is called the CPU bus. A bus, as we saw earlier on the motherboard, is simply a group of wires that connect multiple components inside a computer. On the bus are some other registers with their own set and enable wires. These may have numbers from previous instructions already saved inside. So the control unit will then turn on the set wire of the particular register that it wants to save that number to, and that number will be saved in that register. Afterward, the control unit will then turn off the enable wire from the first register and clear the bus. The 4 registers at the top are just used for storing numbers between operations, so they have output wires that go directly back onto the bus. So now we have moved a number from one register to another just by turning some wires on and off. That's the advantage of the bus, easily moving numbers between components. The disadvantage of the bus is that you can only have one number on it at a time. Because of this limitation, the arithmetic logic unit uses a temporary register for input B. When the control unit is processing an instruction involving the ALU, it will move one of the inputs to the temporary register. The temporary register has no need for an enable wire since it only outputs to the ALU and doesn't conflict with any other registers. The other input to the ALU comes directly from the bus. The control unit will enable another register, and that number will become input A to the ALU. That number stays on the bus until the ALU is finished processing the instruction. And so now there are 2 inputs to the ALU, and we're ready for the ALU to perform an operation. As we saw earlier, the control unit knows what operation to tell the ALU to perform because of the instruction it receives from RAM. The instruction itself is in another register called the instruction register. By the way, the input wires from the bus won't affect this register since the instruction was already saved in a previous step. This register, like the temporary register, also has no need for an enable wire since it just outputs to the control unit. Based upon this instruction, the control unit then tells the ALU what type of operation to perform. So let's say the instruction we're processing is a compare instruction. With the compare instruction, we're not interested in the number that is output by the ALU. We only want to know how the 2 inputs compare to each other. For that, we use the flags that we talked about earlier. Each flag is just a wire that turns on or off depending upon whether or not a certain condition is true. Inside the Scott CPU, there are 4 flags, and we'll look at 2 of them now. The A is larger flag will turn on if input A is larger than input B. If the inputs are the same, then the equal flag turns on, and if both of these flags are off, that means input B is larger. But in this case, the equal flag is on, so that means both inputs are the same. Once the compare instruction is over, we still need to use the flags for the next instruction, so we'll save them to a register that only has 4 inputs and 4 outputs, 1 for each flag. Once the flags are set into the flags register, the CPU is finished with the compare instruction, and it can then request the next instruction from RAM. Generally, the next instruction after a compare instruction is a jump if instruction. This combination of a compare and a jump if instruction, by the way, is very common in computer programming. Anytime there is more than one possible path through a program, the computer is using these instructions to tell it which way to go. So now that we're finished with the compare instruction and our flags are saved in the flags register, we need to tell RAM that we're ready for the next piece of data, in this case the next instruction. So inside the CPU, another register that is very important is what's called the instruction address register. The CPU uses this register to know where the next instruction should come from in RAM. When the CPU is ready for the next instruction, it enables the instruction address register onto the bus. Eventually, the instruction address will flow to RAM, but it doesn't get there directly. There is an intermediary register called the memory address register, whose only job is to tell RAM what memory address the CPU wants next, since it won't always be an instruction. Once the instruction address is set into the memory address register, it is automatically sent to RAM since the memory address register doesn't have an enable wire. The control unit then turns on the enable RAM wire, and RAM automatically sends back the data at that address, which in this case is an instruction. That instruction is then saved in the instruction register, and the control unit begins processing it. In this case, it's a jump if equal instruction, which checks to see if the equal flag is on. It does that by running one of its wires and the equal flag wire into an AND gate. If both inputs to the AND gate are on, then the output wire turns on as well. This output wire will then trigger the jump. That jump eventually retrieves the next piece of data from RAM, which happens to be an address, and move it into the instruction address register. When the jump if equal instruction is over, the CPU then processes the instruction at that new address. At that new address may be some instructions that output the text "you guessed correctly" onto the screen, because now we know that the user guessed correctly. So we'll add the final 4 wires to our CPU, which are used to control the external devices like the monitor and the keyboard. We now have a nearly complete picture of what the Scott CPU looks like. Data moves around inside the CPU using the bus and is stored in each register according to how that data is going to be used. Each instruction that we have seen can be processed by the Scott CPU in about 6 clock ticks. Modern CPUs can process multiple instructions per clock tick, meaning that the computer you're using to watch this video is likely processing tens or even hundreds of billions of instructions per second. That phenomenal speed is accomplished by using more than one of each component and making sure that all the components are active as much as possible. This makes modern CPUs much more complicated than the Scott CPU, but they are still fundamentally doing the same things as the Scott CPU. So now let's zoom back out and we can see all the wires that run back out to the pins on the chip. On the right are the set RAM and enable RAM wires. On the top are the RAM address wires. On the bottom are the data wires that run to both RAM and the external devices. And on the left are the input-output control wires. So let's zoom back out to see the rest of the chip, and we'll put the cover back on the CPU.
Hello everyone, and welcome to this video. We're going to be talking today about what a register is. We're going to have a couple examples. I'm not going to explain all of them for lack of time, but the most basic function I will describe and define on those. So what is a register? A register is basically a group of flip-flops that are hooked together to hold certain aspects of data. So usually we're going to use in D flip-flops in the examples that we have here, but I guess that is what a register is. Now, what do we use a register for? A register, like we said, can be used for data storage, so we can use it to store data for further use. For instance, you can hold numbers in order to add them later, subtract them later, multiply them, or even display them on a LCD, for instance, if you have that kind of programming in your circuit or your processor. Data can also be transferred. Due to the fact that it is stored, it can be transferred from one register to another without losing the data. Now let's see a couple examples of registers in order to see what they do. These are one of the more simpler ones. We have remember in these flip-flops, each bit requires a flip-flop, and in each flip-flop, in this case, Q follows D. Of course, in the shift to the left example, you can see that the first D follows Q, but that Q follows the last D. So it's really not that complicated of an issue. It's just Q will always become what D is. So D is the first state, and then you input it, and then Q outputs that. So we put in our first input there, and now we have the most significant bit to the least significant bit, which is x0. Remember, the clock does not affect really whether it shifts from left to right. It is the hookups between the D's and the Q's here. Now let's look at this register. This register is a loadable 1-bit register in that it has an input, the D in. It has a load switch that says, do I want to load the old value, or do I want to load in the new value? If load is 0, then it's going to take that Q, which is this is the old value, the register with the old value, and it will take that and it will say, okay, so that is the old value. Let's put the old value back into that register. Just keep cycling through. If it's 1, you're going to say, you know what? I kind of want this guy loaded in there, and that is going to be contained there, and it will wait for you to, it'll cycle back, and now it'll wait for you again to say, okay, do you want to load that new value back in again, or do you want to put an even newer value in? Now, once again, registers aren't the most complicated thing in the world, but they can get pretty complicated when you reach the capacity of a register file. So let's talk a little bit about that. A register file is an array, or basically kind of a string of registers together in one unit. So it can contain multiple numbers, and these numbers are going to do different things. They can be held together for math equations or for displays, as we said before. Here's an example. I couldn't really give you gate level just because this may become part of your final, and I don't want to give too much away there. But here we have a register file. We have 2 registers. Each register will hold a 4-bit, as we see from D0 to D3, it will hold a 4-bit number. And we see that the clocks are connected, and there is a write enable switch, which will allow it to be manipulated or moved or printed out on an LCD screen, or sorry, display. And those are the outputs. Now, generally, a register is going to be ALUs and muxes and other things are going to have registers because they also need to store data. But a register file may receive data that is stored in those functions and then be used to either be spit back into those functions, or it will be used in order to be shot to a display or just held there. For instance, if I were to have an ALU will have a register because it needs to hold a number. In the case of multiplication or something like that, it will need to have its own register file to store data. But let's say I want to take from the ALU and I want to spit into the register a 3, let's say, and I have a 6. So I would load a 3, and I would get a 3 from the ALU, and I would add the 2 3 with the ALU, making a 6, and then I would say, okay, you know what, I want to load the lower register with a 6, and I want to load the higher register with the same value I had before, and I will we'll spit that number to the ALU and add that together. 3 plus 6 would be 9, and that way you can do even multiplication if you want. You can do addition, subtraction, all through simple use of a register file and an ALU. You would obviously need a mux for a bridge point, but that's kind of besides the point. Just remember, registers are for holding data, one flip-flop per bit. They can contain several options, including write enable. They can include a load function, an enable input function, a shift enable, and it really depends on the way that you'll design them. But just remember that what they're for is storage, and what they're used for is data transfer and storage, and that they all need to be on the same clock, and that D will follow Q in most cases. And I guess the best way to learn about them is just kind of using them and playing with them in Xilinx, which you probably won't have a ton of time for, but in the labs you will be able to learn what a register does and a register file does in your final lab. So good luck to all of you, and I hope this has been of some help. Registers are definitely going to be a useful thing in your career, whether it be in software design or hardware, whatever. So try and pay attention to this part of the course.
MID is the processor register. In computer architecture, a processor register is a small amount of storage available as part of a CPU or other digital processor. Such registers are addressed by mechanisms other than main memory and can be accessed more quickly. Almost all computers, load store architecture, or not, load data from a larger memory into registers, where it is used for arithmetic, manipulated, or tested by some machine instruction. But cache is without doubt the most important thing you can have in your processor. It really does improve the performance of your system. Let me show you how it does it. Now we have a good little diagram here. There is processor, cache, cache controller and RAM. The cache can do something called reading ahead. Let me describe you what does that mean. Here in RAM, files are broken into little blocks, generally into 64 kilobytes blocks of RAM. Let's imagine we have opened a file, and we start reading it. The first thing the CPU does is to search for the file in cache, but of course the cache doesn't have it. That is called a miss. So in the second process the CPU goes to RAM and finds it in there, but it can bring over only one block at a time. So it grabs hold of that block, transfers it back to the CPU, and it starts working on it. And this is where the intelligence kicks in, because the cache controller makes a very good assumption that if I use that particular piece of code related to that file, I might need the rest of the code related to the file at some point very shortly in the future. So the cache controller grabs hold of the rest of the file and moves it to the cache. When indeed the CPU needs to find the rest of the information, it searches first the cache, and it finds it in there. That saves it from having to go to RAM at all. The main question here is why the CPU just doesn't go to RAM, and there is a very simple reason for this, because cache is much faster than RAM. Now you remember that blocks of code is moved from RAM to cache, and that's where the replacement policy decides where in the cache a copy of a particular entry of main memory will go. But when the cache is full, a replacement algorithm must choose which items to discard to make room for the new ones. If the replacement policy is free to choose any entry in the cache to hold the copy, the cache is called fully associative. At the other extreme, if each entry in main memory can go in just one place in the cache is direct mapped. Let's begin with fully associative mapping. Its approach is to store both memory address and data together in the cache. A fully associative cache requires the cache to be composed of associative memory holding both the memory address and the data for each cache line. The incoming memory address is simultaneously compared with all stored. If a match is found, the corresponding data is read out. Single words from anywhere within the main memory could be held in the cache, if the associative part of the cache is capable of holding a full address. In all organizations, the data can be more than one word, that is, a block of consecutive locations, to take advantage of spatial locality. In the figure, a line constitutes 4 words, each word being 4 bytes. The least significant part of the address selects the particular byte, the next part selects the word, and the remaining bits form the address compared to the address in the cache. The whole line can be transferred to and from the cache in one transaction if there are sufficient data paths between the main memory and the cache. With only one data word path, the words of the line have to be transferred in separate transactions. The fully associate mapping cache gives the greatest flexibility of holding combinations of blocks in the cache and minimum conflict for a given size cache, but is also the most expensive. It requires a replacement algorithm to select a block to remove eponymous, and the algorithm must be implemented in hardware to maintain a high speed of operation. As we said, there is another mapping method called direct mapping. The fully associative cache is expensive to implement. In direct mapping, the cache consists of normal high-speed random access memory, and each location in the cache holds the data at an address in the cache given by the lower significant bits of the main memory address. This enables the block to be selected directly from the lower significant bits of the memory address. The remaining higher significant bits of the address are stored in the cache with the data to complete the identification of the cache data. Consider the example shown in the figure. The address from the processor is divided into two fields, a tag and index. The tag consists of the higher significant bits of the address, which are stored with the data. The index is the lower significant bits of the address used to address the cache. When the memory is referenced, the index is first used to access a word in the cache. Then the tag stored in the accessed word is read and compared with the tag in the address. If the two tags are the same, indicating that the word is the one required, access is made to the address cache word. However, if the tags are not the same, indicating that the required word is not in the cache, reference is made to the main memory to find it. For a memory read operation, the word is then transferred into the cache, where it is accessed. Here is the direct map cache with a line consisting of more than one word. The main memory address is composed of a tag, an index, and a word within a line. All the words within a line in the cache have the same stored tag. The index part to the address is used to access the cache, and the stored tag is compared with required tag address. For a read operation, if the tags are the same, the word within the block is selected for transfer to the processor. If the tags are not the same, the block containing the required word is first transferred to the cache. There is a third type of mapping called set associative mapping. Its scheme combines the simplicity of direct mapping with the flexibility of fully associative mapping. It is more practical than fully associative mapping, because the associative portion is limited to just a few slots that make up a set. The organization is shown in the figure. The cache is divided into sets of blocks. Each block in each set has a stored tag which, together with the index, completes the identification of the block. First, the index of the address from the processor is used to access the set. Then, comparators are used to compare all tags of the selected set with the incoming tag. If a match is found, the corresponding location is accessed. Otherwise, as before, an access to the main memory is made. The tag address bits are always chosen to be the most significant bits of the full address, the block address bits are the next significant bits, and the word address bits form the least significant bits, as this spreads out consecutive main memory blocks throughout consecutive sets in the cache. Notice that the association between the stored tags and the incoming tag is done using comparators, and can be shared for each associative search, and all the information, tags, and data can be stored in ordinary random access memory. The number of comparators required in the set associative cache is given by the number of blocks in a set, not the number of blocks in all, as in a fully associative memory. The set can be selected quickly, and all the blocks of the set can be read out simultaneously. After a tag has been identified, the corresponding block can be selected. The replacement algorithm for set associative mapping considers the lines in one set, as the choice of set is predetermined by the index in the address. Hence, with two blocks in each set, for example, only one additional bit is necessary in each set to identify the block to replace. Now let's talk a bit about the problems that occur. When a data is written to the cache, it must at some point be written to the RAM as well. The timing of this write is controlled by what is known as the write policy. In a write-through cache policy, every write to the cache causes a write to the RAM. Alternatively, in a write-back cache, writes are not immediately mirrored to the store. Instead, the cache tracks which of its locations have been written over. These locations are marked dirty. The data in these locations is written back to the RAM when those data are evicted from the cache. For this reason, a miss in a write-back cache will often require two memory accesses to service, one to retrieve the needed data, and one to write replaced data from the cache to the store. The probability that the required word is already in the cache depends upon the program and organization of the cache. Typically 70 to 90% of references will find their words in the cache, called a hit, but the rest is when a reference to the main memory is necessary, called a miss. The hit ratio of a cache describes how often a searched for item is actually found in the cache. More efficient replacement policies keep track of more usage information in order to improve the hit rate for a given cache size. The latency of a cache describes how long after requesting a desired item, the cache can return that item when there is a hit. Faster replacement strategies typically keep track of less usage information. Or, in the case of direct mapped cache, no information at all, to reduce the amount of time required to update that information. The average memory reference time, as you can see, is a sum of the miss ratio multiplied with the time to make access to RAM, plus the time to reference the cache, if there is a hit, and last, some time for various secondary effects. If there is a hit in the cache, the first part becomes 0, and, as you can see, the memory reference time significantly drops. In other words, from top to bottom of the pyramid, every memory is a subset of the next in the hierarchy. The faster the memory is, the pricier it goes. But don't worry. Today's technology advances faster than it is expected, so prices are going down with each pass.
In Section 1, we talked about secondary memory, which is permanent storage. This dealt with hard drives. Now we'll talk about primary memory, or temporary storage. This is called RAM. RAM stands for Random Access Memory. In order for data or a program to run, it needs to be loaded into RAM first. So here is how it works. The data or program is stored on the hard drive. Then from the hard drive, it is loaded into RAM. And once it's loaded into RAM, the CPU can now access the data or run the program. Now, a lot of times, if the memory is too low, it might not be able to hold all the data that the CPU needs. And when this happens, then some of the data has to be kept on the hard drive to compensate for low memory. So instead of data going from RAM to the CPU, it has to do extra work by going back to the hard drive. And when this happens, it slows down the computer. So to solve this problem, all you need to do is increase the amount of RAM on the computer. And by increasing the memory, all the data can be loaded into RAM without the need of constantly accessing the hard drive. And the result is a faster performing computer. RAM requires constant electrical power to store data, and if the power is turned off, then the data is erased. RAM is stored on the motherboard in modules called DIMMs. These DIMMs come in different memory sizes. Today, they range anywhere from 128 megs to 4 gigs of memory per DIMM or more. RAM also comes in different types, such as dynamic RAM or DRAM. DRAM is memory that contains capacitors, and because it has capacitors, it has to be refreshed often. SRAM stands for synchronous RAM. This memory uses transistors and does not have to be refreshed, unlike DRAM. And because of this, it is much faster than DRAM. and it is also very expensive. An example of SRAM would be the memory cache level 1 and 2 that is used by the CPU. Another type of memory is called SDRAM, which stands for Synchronous DRAM. This type of memory is what is used today in RAM DIMMs. The difference between SDRAM and DRAM is basically speed. The older DRAM technology operates asynchronously with the system clock, which basically means that it runs slower than the system clock because its signals are not coordinated with it. But SDRAM runs in sync with the system clock, which is why it is faster than DRAM. All the signals are tied to the system clock for a better controlled timing. SDRAM is rated at different speeds. For example, a stick of SDRAM could be labeled PC100. The 100 equals the speed at which it operates, which is 100 megahertz. And since SDRAM only comes in 64-bit modules, it has an 8-byte wide bus, because 64 divided by 8 equals 8. So to figure out the total bandwidth of PC100, you multiply 100 megahertz times 8 bytes, which equals 800 megabytes per second. So the total bandwidth of PC100 equals 800 megabytes per second. So an SDRAM module labeled PC133, you multiply 133 by 8 bytes, which equals 1066. So the total bandwidth for PC133 equals 1066 megabytes per second. As technology increased and processor and bus speeds have gotten faster, a new RAM technology was developed to keep up with the faster speeds of computers. This newer technology was called DDR, which stands for double data rate. And that's basically what DDR does. It sends double the amount of data in each clock signal when compared to non-DDR RAM. Non-DDR or single data rate RAM uses only the rising edge of the signal to transfer data. But DDR uses both the rising and falling edges of the clock signal to send data, which makes DDR twice as fast. DDR is also labeled differently than non-DDR RAM. Instead of including the clock speed in its name, like PC133, where 133 equals the clock speed, DDR uses the total bandwidth instead. For example, a DDR DIMM labeled PC2700. The 2700 is not the clock speed, but it's the actual total bandwidth. The clock speed for PC2700 is 333 megahertz. So 333 megahertz times 8 bytes is rounded off to 2700 megabytes per second, which is where we get the name PC2700. Another example is PC3200. PC3200 has a clock speed of 400 megahertz. So 400 times 8 equals 3200, which is where we get the name PC3200. A new technology that has succeeded DDR is DDR2. DDR2 is faster than DDR because it allows for higher bus speeds, and it also uses less power than DDR. A DDR2 DIMM has 240 pins, compared to 184 pins on DDR. Some examples of DDR2 are PC2 3200 and PC2 4200. And the latest RAM technology is called DDR3. DDR3 is twice as fast as DDR2, with a bandwidth of over 12,800 megabytes per second. Like DDR2, a DDR3 DIMM also has 240 pins. but the notches in the DIMMs are in different places. So you can't put a DDR3 DIMM in a RAM slot made for DDR2. In fact, motherboards are made to support a certain type of memory, so you can't mix DDR1, 2, or 3 on the same motherboard. Some examples of DDR3 are PC3 8500 and PC3 12800. Another type of memory was called RDRAM, which was developed by Rambus Inc. And they developed the RIM, which stands for Rambus Inline Memory Module. RIMs have 184 pins and look similar to DIMMs, with the exception that the bottom notches are located in the center of the module. In 1999, RIMs were a breakthrough in the speed of memory, but has quickly fallen behind due to the advancement of technology in DIMMs. When RDRAM debuted in 1999, it ran at 800 MHz, which was considerably faster than SDRAM, which ran at 133 MHz at that time. But even though it was a lot faster than SDRAM, RDRAM only had a 2-byte wide bus, compared to SDRAM, which had an 8-byte wide bus. So if you multiply the speed of RDRAM, which was 800 MHz, times the bus width, which was 2 bytes, you would get a total bandwidth of 1600 megabytes per second. RIM technology was designed to work with a continuous signal, which means that all the other memory slots on the motherboard must be used for RIMs to work properly. And if other RIMs are not available, then a user can install a CRIM or continuity RIM, which is basically a dummy RIM to ensure continuity in all the memory slots. To meet the higher demands of faster processors and memory controllers, a new technology was developed called dual-channel mode. Dual-channel mode requires a pair of identical DIMMs installed on the motherboard, which allows the memory controller the ability to communicate with 2 DIMMs simultaneously, which increases the speed of...
Now let's talk about how virtual memory works. And we're going to introduce 2 concepts here: virtual and physical addresses, and some acronyms for them. So how does virtual memory work? The basic idea is we have these separate memory spaces. So virtual memory is what a program sees, and physical memory is the physical RAM in the computer. So when you install memory in your computer or you buy a computer with memory, this is what you're paying for. What the program sees, the virtual memory, this is what the ISA promises. So remember, in MIPS, this promises the virtual address. So if we do a load R4 1024R0, this is going to access a virtual address 1024. So the MIPS ISA promises a certain virtual memory address space, but the physical memory is what you have in your machine. So if you have 2 gigabytes of RAM installed, you're going to have physical addresses from 0 to 2 to the 31 minus 1. That's 2 billion bytes of memory. So virtual addresses, or VA, we're going to abbreviate them virtual addresses VA, this is what the program uses. And in MIPS, it's a 32-bit address space. The physical addresses, or PA, is what the hardware uses to talk to the RAM. And this is determined by how much RAM you have installed. If you only have a little bit of RAM installed, your physical address space, or your PA, is going to be small. If you have a lot of RAM, it's going to be big. But now we have separate address spaces here. So each program is going to have its own virtual address space, and we have a physical address space for our memory. So how do we make this work? How does a program access memory? So the program executes a load, and the load is going to specify a virtual address because that's the way programs work. So here's our processor, it's running the program virtual address space, and here's our load. So load R3 1024R0. What's the physical address going to be here? Or sorry, virtual address? Well, it's just going to be 1024. So the processor is going to access virtual address 1024. That's what this instruction is going to do. Now, the computer is going to translate this virtual address to the physical address in the memory. So we're going to have a translation here. This is our map from virtual address to physical address, and it's going to tell us how to get the data over here. So here's the data we want for R3. This map is going to tell us how to get there. So we go ahead and tell the translation, or the map here, we want virtual address 1024. It looks it up in its map. It says, oh, well, virtual address 1024 maps to physical address 2. So it goes over here to physical address 2, and it goes and gets the data. Now, if the data is not in memory, it goes and loads it from disk. In this case, it is in memory, so we're going to take this data here, and we're going to return it. So we took virtual address 1024, translated it to physical address 2, and now we send this back so we get the data. Now we go ahead and do another instruction. This instruction here is going to load virtual address 512. So we go over to our translation, ask it where 512 goes. It says, hey, it goes to physical address 12. So we go down to physical address 12 here, go ahead and get our data, and we send it back. Now we do another instruction. This is an add instruction. It's just using registers, so we don't need to do any translation here. And then we go and we have another instruction. This is going to access virtual address 786. So we go to virtual address 786. The map tells us it's on disk. It's not in memory. Okay, it's on disk. So what do we need to do to get it? Well, we need to load it into memory. So we go ahead and load this data into memory. Once we've loaded it in memory, now we go and update the translation map. Okay, so now we no longer want to translate address 786 to disk. We want to translate address 786 to this location in memory. So we update that to 4. Now when we put in virtual address 786, we get out physical address 4. We go ahead and load it from data, from the memory, and we return the value. So program executes and load with a virtual address. The computer translates it into the physical address. If it's not in memory, we get it from disk. And then the computer reads the RAM using the physical address and returns it to the program. That's how virtual memory works. So a question, what address is located here? So address R12 has the value 1536, and the program issues this load. What location in RAM is going to be accessed? Well, we need more information here. The program is accessing virtual address 1536. That's what this is going to do here. But we don't know what physical address that's going to be. So here's our processor. It's in the program's virtual address space, and we do this load. This load is going to generate virtual address 1536, but we're going to have a map, and the map's going to tell us which physical address it is. Now, if I don't tell you what the mapping here is, you have no idea what location in RAM this address is going to access. So we need more information to know what memory we're actually going to access when we issue this instruction. So here's another question about using too much data. If a program uses more data than can fit into RAM, where does the data go? Well, it's going to go to disk. If it doesn't fit into the memory, we're going to use virtual memory to map it to disk. So here's a load. Say this load's going into our table, and we didn't have enough space in memory, in physical memory, for this virtual address. The translation table, the map here, will tell us that it's on disk, and we'll know it's on the disk. And so we can put the data on disk if it doesn't fit into memory.